Let's take a look at this second problem in your quiz that goes with free body diagrams of rigid bodies. It's this funny looking upside down truss, and that might seem a little bit weird. So here is a free body diagram of that truss with the forces and the reactions and the distances. The book gives you these heights, but we don't care about that. Those heights do not matter. It's what they call a red herring. It doesn't matter. In fact, this is just a funny shaped beam. And if you wanted to, you could just draw a beam like this with a rectangle. Or you could leave it this shape if you wanted to. It doesn't matter. You're going to get the same answer using the same exact process, no matter what funny shape your beam is. So let's look in your toolbox, your 3 equilibrium equations, and you probably by now are familiar with the idea that we'll probably start with sum of all moments equals 0. So if we're going to use moments, let's make sure we're clear about what direction these moments are going to turn. So we've got, oh, and let me just say, I know we've said this about the K before, but we'll say it again. K stands for 1,000. And when engineers want to write 1,000 pounds, they just write K. So that's why you don't see the pound abbreviation here. 2K stands for 2,000 pounds. Okay, moment directions. So we've got 2,000 pounds going clockwise, so that's a negative moment. 3,000 pounds going clockwise, so that's a negative moment. 4,000 pounds going clockwise, so that's a negative moment. And the reaction at B turning counterclockwise, so that's a positive moment. All right, let's do the moments. And we're going to take moments around point A, because that's convenient. So we'll write sum of all moments around A equals 0, because this thing is in equilibrium. And just a reminder, what is our moment equation? Moment is force times distance. So let's just chug across here and do force times distance, and so forth. What's the first one we come to? We've got 2,000 pounds times a distance of 20 feet, and that's a negative moment because it's clockwise. Then we come to the 3,000 pounds. What is the distance there? It's not 20. What is the distance from point A? It's 40 feet from point A to this force, and that's a negative moment. What about the 4,000 pound force? It's not 20 feet, it's 20, 40, 60 feet from point A, and it's clockwise moment, so it's a negative moment. And then we've got another moment caused by the reaction at B, and that's 20, 40, 60, 80 feet, and that's counterclockwise, so that's a positive moment. And what does that all add up to? It all adds up to 0. So now let's get our friend the calculator and smush some of these numbers together. If we do all of these numbers, we find out they all add up to negative 400,000 foot-pounds. And then here's 80b foot-pounds, and that all adds up to 0. So we could add 400 to both sides. That would get this 400 out of here, and that would move a positive 400 to the other side. So that leaves us with 80b equals 400,000. Now we can divide both sides by 80, and we are left with, let me see, 400,000 divided by 80 gives us B equals 5,000. So now we can write 5,000 up there by B. That's that reaction. Now, what shall we do? Let's look in our toolbox and let's find the sum of all forces in the y direction equals 0. We'll use that. So sum of all forces in the y direction equals 0. Sum of all forces y equals, what have we got? We've got A going up, so it's positive. 2,000 coming down, so it's negative. 3,000 coming down. 4,000 coming down. And 5,000 going up, so it's positive. And what does that all add up to? It all adds up to 0 because this thing is in equilibrium. All right, so let's get our calculator again and smush all these numbers together. -2, -3, -4, +5. We come up with, we've still got our A there. We come up with plus A minus 4, or minus 4,000, equals 0. Let's add 4,000 to each side. The 4,000s cancel out, and we're left with A equals 4,000. And that is the answer. Yay!